Good evening, everyone.
Good evening, ma'am.
Good evening, ma'am.
Yes, yes. Very good evening. Okay, students, I just want a couple of minutes. I just had a class. I just need to drink little water. Just give a couple of minutes. After which, uh, we will continue our discussion. So I need a few minutes. And meanwhile, you can correlate what we discussed about silicones and silicates. Fine. Good evening. As I just now mentioned, I need a couple of more minutes, and then I'll just start. Fine, everyone. I'll just go to the restroom, drink water, and then we'll start. Thank you so much for your patience. I was literally hurrying to eat and then I couldn't drink water that I'll drink now also again. So thank you so much again, and now we will start our discussion further. Everyone there, right? Right. All of you are there. Nitrogen family, one family coming and going. Boron family, carbon family, and now, right now, nitrogen family. Group 15. So what we have here is
Ma'am, screen is not share.
nitrogen. Let's see the family members now. Everyone, yes. I hope you can hear me. You can see the screen. Oh my god. Oh my god. I know what I did. I didn't share the screen. Yeah. I started mentioning the names of the family members. Yes, without sharing the screen. Now I've shared the screen. Yes. So you have all the nitrogen family members. We have nitrogen, phosphorus, arsenic, antimony, bismuth, and what is this? Moscovium, the new element. The general electronic configuration is Ns2Np3. Students, tell me the speciality of this half-filled configuration. Everyone here knows. The capacity of p orbital is maximum 6 electrons. Yes. So, if I compare the ionization energy of nitrogen versus oxygen, I mean the first ionization energy, I have to specify. Yes. So nitrogen's first ionization energy will be more. What about its electron affinity? Would it like to gain an electron? It would not like to lose, you just now mentioned. So ionization energy means the tendency to lose the energy required to lose its outermost electron. Electron affinity is also this because it's quite stable. It's happy the way it is, right? Yes, yes, yes. Very good. So it has Ns2Np3 configuration. So what we have here is nitrogen, phosphorus, arsenic, antimony, bismuth, moscovium. Nitrogen and phosphorus are non-metals. Arsenic, antimony, metalloids. Bismuth, metal. Yes, moscovium, we are not. It's like there in the first slide. Happens to in movies, their name is there in the list, but hardly some role comes in that sequence of like whatever series or episodes are there like that. Yes. So nictogen means suffocating. So because of their suffocating odor or what, leave it. You're not much bothered. So it's also known as nictogen family, Ns2 Np3 configuration. Physical state. Everyone knows N2 is a gas. Students, again, since you have learned about back bonding in this whatever discussion we started from yesterday, right? Yes. So, can you correlate and think why N2 exists but P2 does not? When you answer this, I can drink little more water. Don't know what food I had today. So much of water I'm drinking. Anyways, tell me, why does N2 exist? And that also is a fine, it exists as a gas, but due to phosphorus has three p orbitals. So when N2 is formed, there's a triple bond. Means 2p forms 1 sigma and remaining 2 pi bonds. For formation of pi bonds, they have to overlap sideways. For sideways overlap, they have to come closer. They can come closer if they are small in size. Phosphorus is comparatively large. 3p orbitals are quite larger. So effective pi overlap or sideways overlap is not possible. Similar reasons, remember AlCl3 cannot form back bonds because the filled 3p of chlorine is large. The filled 3p of chlorine is large. The vacant 3p of phosphorus is also large. So 3p is large. Similarly, 3p is large here and hence a minute. 1 minute. Yes. So effective pi bonding would not be possible. The first element, nitrogen, is a gas. This gives me feeling of that Amul butter like thing, right? Correct, no? It's a soft, waxy solid. I'll just drop P4. Phosphorus exists as P4, and then you will understand. When I draw N2 and P4, can you comment on the hybridization of P4 here? Very good. One lone pair, three bond pairs. It's sp3 hybridized. Everyone knows the sp3 hybridization expected bond angle is
109 degrees.
109.5. And yeah, I do agree. I have to agree. Yes, 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 yes. So many answers. Thank you so much. So, yes, the expected bond angle is 109.5. But there are all bond pairs. Let me correct myself. When there's a lone pair, due to lone pair bond pair repulsions being more than bond pair repulsions, I see the bond angle less than
Decreases.
109.5. Anyways, how much less it should be? Like ammonia is 107, water is 104.5. But here, do you know what is the angle here? You won't believe, 60 degree. How much of angle strain is there due to difference between the expected and the actual bond angle? So much of strained molecule, right?
Yes.
Yes, so much of strain is there. As a result of which, the molecule is highly reactive, highly unstable, and this triple bond, not one, not two, three people are there together. Together, it's very strong bond. It has a very high bond dissociation energy. Fine. That's the reason N2 exists as a gas. P4 exists as a soft waxy solid, and it's highly unstable because of the high strain in the molecule, but the difference due to the difference between the actual and expected bond angle. The remaining elements are solids, so they are hard and they possess metallic luster, the shine. Why N2 is inert at room temperature, but phosphorus is highly reactive. N2 has a high bond dissociation energy, difficult to break it, so it's inert. That's the reason our 78% of the atmosphere contains N2 gas, but still, under ordinary conditions, it doesn't react. Under what conditions N2 reacts with O2, students? Under what conditions? Think. N2 reacts with O2 under what conditions? Very high temperature. No. Yes, high temperature. Thunder, lightning, thunderstorm, there's lightning, no? At very high temperature, N2 and O2 will react to form. Yes, high temperature, correct. N2 on O2, very high temperature, thunder, lightning, that time. It will form NO. Little bit, let me illustrate. N2 and O2. Would be a part of this chapter also. Very high temperature. Thunder, striking of an electric arc. It will first form NO. Today morning only you told me, no, NO is a neutral oxide. Very good. But NO is again highly unstable. Students, is NO an example of odd electron molecule?
Yes, ma'am.
Yes, no? Nitrogen says I have one, two, three, four, five valence electrons. And oxygen says I have one, two, three, four, five, six. So this will bond, this will bond. And what will happen? Wait, where do I write? Let's see the place, huh? So what will happen? N, this two intact, O, this two intact, and these two normal bonds, and remaining two from oxygen and one from nitrogen. So you can clearly see on nitrogen presence of this unpaired electron, which makes it para or diamagnetic. Tell me.
Paramagnet.
Very good, very good.
Paramagnetic.
Para. Good enough. So it's highly unstable. That's what I mean. So do the structure also. We have oxides of nitrogen also in this chapter. Now this NO combines with oxygen. So now NO combines with oxygen to form NO2. NO combines with oxygen to form NO2. NO2 is much more stable, right? Yes. By the way, NO2 is paramagnetic or diamagnetic? NO is paramagnetic. Fine, justified. NO2, think, think. A coordinate bond. Hey, you need not be sorry. Please, students, it's okay. I go wrong also. It's I okay. I feel fine. Yeah, we are all a family. So by the way, nitrogen is behaving as a donor. So this electrons are nitrogens 1, 2. Now 3, 4. This is also nitrogens. And the fifth one here alone. Again paramagnetic. Reddish brown in color. Acidic in nature. So NO2 is formed. Now NO2. NO2 will combine with rainwater. This all happens in the atmosphere. So when NO2 combines with rainwater, what do we get?
Acid rain.
Actually, we get HNO3 plus HNO2. HNO2 being unstable decomposes giving NO. So again, NO combines with O2, NO2. So basically, yes, the main stable component is HNO3. Faizan, yes, I'll agree. So, and HNO3 hence in that way contributes to acid rain. So all the chapters are in a other way correlated. But let's go step by step, slide by slide. Yes. So P4 has a lot of angle strain. It's highly unstable. N2, due to its large bond dissociation energy, it is inert at room temperature. It's stable, it's inert. This P4 is so unstable that oxygen is around, right? It will undergo slow combustion. And that's the reason. Reaction would be exothermic, of course. All combustions are exothermic. So that's the reason you can see it glowing in the dark. So even at room temperature, slow combustion will take place when it's exposed to air and hence it glows in the dark. So in this discussion, only two oxides of nitrogen, NO and NO2, we have discussed the structure. So every discussion has a relevance, it has a point. Nitrogen, you have an anomalous behavior. What comes to your mind when you think about this? The first thing which only comes to my mind is the absence of, correct, same. Arpita, wait, I'll ask others. Voice lag only with Arpita or with others also? Please specify. I don't realize from here. It's all right. Faizan says, fine for Karthik also. Okay. Happens sometimes with individual network issues and sometimes happens from here also. Okay, so we have to get. Okay, fine. Thank you. Thank you for responding. Arpita, let me know. Let me know. Otherwise, we'll wait for you. You can just log out and log in again. So sometimes such issues are resolved only by doing this. Let's see. You let me know. Okay. So nitrogen, yes, you are belonging to the second period. So you don't have a d orbital to expand your octet. So agreed. You have a small size. You have high electronegativity, and suppose you are bonded to hydrogen, like you suppose in the form of ammonia. You can also show hydrogen bonding. Let's see. Yes. The first member actually for all the groups differs from the other members due to its small size, high ionization energy, half-full orbital I said, high electronegativity. Yes. After fluorine and oxygen, the next most electronegative element is nitrogen. Nitrogen and chlorine almost have similar electronegativity values, right? Yes. And because of the small size, it can easily form multiple bonds, which is not seen in the case of the other elements of the group because of the large size of their orbitals. And as mentioned here again, the same thing. The heavier elements do not form pi bonds. As mentioned, non-availability of the d orbitals. Yes. Small size because of which it can form multiple bonds easily. Okay, so this is the reason NCl5 can't be formed because nitrogen cannot expand its octet. It's small in size, so it can form multiple bonds easily. That's not possible for other elements to form multiple bonds like this. Due to its high electronegativity, compounds like ammonia can exhibit hydrogen bonding. Ease of formation of multiple bonds. Again, small size, hence sideways overlap of the p orbitals, that's two p orbitals is easy. Fine. Atomic radius. Wait again. Normal trend, students, normally increases. So atomic radii increases with increase in atomic number usual. You can see from the way they have shown the atom's size. That's good enough for us to understand. And the values also must have been mentioned. You need not remember the values. You just remember the trends. So you can see a regular increase. So no confusion, no problem. Ionization energy. You can see a regular decrease down the group. Just once again check the values. So size increases regularly down the group. The size increases. The ionization energy decreases regularly down the group. No confusion, easy, perfect. All right. Yes. No anomalous behavior. Catenation. Students, if this word catenation comes, the first thing which comes to our mind is yes, the element which can show, if we just forget group 14 for the time being, I'm sorry, 15 for the 15 for the timing, and go to yes, self-linking of atoms, and the best example of that is carbon because of this catenation tendency. And what we have to do because of this catenation tendency, there's another branch of chemistry, organic chemistry, what we have to discuss. Yes, Arpita, Hina, Atika, Faizan, Nandana, everyone. Yes, it's carbon. But when we have left website bye bye to group 14 and come to group 15 here, out of nitrogen and phosphorus, what or which one do you think should have greater tendency? Phosphorus. Why not nitrogen? What's the problem with nitrogen? Phosphorus is highest. True. What a good answering. Lack of d orbitals or d orbitals for normal sigma bond formation. Won't this be good enough? Students, one of the valid reasons I think is nitrogen is small in size. And when nitrogen is small in size, the lone pair of electron, there's a lone pair on each nitrogen, right? So the lone pair of nitrogen, that's quite close. Nitrogen is small in size And the correct. The lone pair repulsion. Mainly the lone pair repulsion, because because of small size, the lone pairs are quite closer, and the extent of repulsion is more. Extent of repulsion is more means they would not like to link with each other. If by linking the lone pair repulsion is increasing, the stability is decreasing. It's better to bond with phosphorus, because though it also has a lone pair, but the size being large, the distance is more, the extent of repulsion is less. Very, very good answering by all of you. Yes, students, that's the reason this self-linking is known as catenation. This ability to self-link, self-bond, that's known as catenation. And this tendency decreases down the group due to increase in the size of the atom. Yes, and this interelectronic repulsion may more in nitrogen due to its small size. Phosphorus catenation tendency is maximum. Okay, yes, the answer is phosphorus. Okay, so many people answering, interacting. Yes, I'll see the time and portions and all, because I want to discuss some questions also. Anyways, let's see. First, let's try to complete P block. Oxidation states. When we talk about oxidation states, what comes to our mind? Inert pair effect. Bismuth will show. Bismuth will be more stable in the +3 state. That's it. Nitrogen can show a variety of oxidation states, starting with -3 in ammonia to +5 in N2O5. The stability of +5 state decreases, whereas that of +3 state increases due to inert pair effect. The stability of +5 state decreases, while +3 oxidation state increases due to inert pair effect. So bismuth here will show inert pair effect. So bismuth will have +3 state more stable than the +5 state. Students, HNO2. Forget, we'll see whatever is written here later. Can you people tell me this HNO2 will act as an oxidizing agent or reducing agent, or what? Very good. Very good. Yes, and the +5 oxidation state stability will decrease. +3 state oxidation state stability will increase due to inert pair effect. Yes, if we call this as a number line, where here we have +5, HNO3, nitrogen is +5. And we have here NH3, where nitrogen is -3. What happens here is HNO2. By the way, what's the oxidation state of nitrogen in HNO2? Who is going to help me out? Okay, excellent. +3. So +3 can lose electrons and become +5, and gain and go to the side also. Since it's here having an intermediate oxidation number, not any of the extremes, it can act as both oxidizing agent as well as reducing agent, and that's proved here. That's the reason, as it's mentioned here, other than the extremes, the oxidation states can show disproportionation. Means HNO3 can get oxidized as well as reduced. This process here is loss, +3 to +5 is loss. That's oxidation. +3 to +2 is gain. reduction. What's given here? In case of phosphorus, nearly all intermediate oxidation states is proportionate into +5 and -3. Let's see. This means if I have H3PO3, it is proportionates into H3PO4 and PH3. I know this reaction. That's it. That's the reason. So your phosphorus acid is undergoing a disproportionation to phosphoric acid, so +3 to +5, as well as +3 to -3. Fine. So it's simple. The intermediate model of the story, the intermediate oxidation numbers can act as both oxidizing and reducing agent. But what are the products? A little bit be careful about the nitrogen and the phosphorus family. That's it. Not family. I mean, they're the same family. In the family, just bother about these two family members more: nitrogen and phosphorus. These two family members are much more important. I think so. H3PO2. This proportionates into H3PO4. Fine. I'll ask you another question, not this disproportionation one. Wait, H3PO2. What is its N factor? Must be knowing, but still. Let's see the chats. Again, all correct answers. Yes. Because that hydrogen which is directly bonded with oxygen is replaceable. That hydrogen which is directly bonded with oxygen can be easily removed as SH plus acidic hydrogen. So its N factor is 1, not 3. Very good. -3 in ammonia. -2 in hydrazine. -1 in hydroxylamine. Hydrozoic acid. -1/3. 0 in N2. +1 in N2O. +2 in NO. +3. NO2 +4. N2O5 +5. See, shows a variety of oxidation states. Oxides of nitrogen. We have already discussed paramagnetic NO. Yeah, as I was mentioning, we have already discussed paramagnetic NO, paramagnetic NO2, and others. Let's see. Limited quantity supply of oxygen, it forms trioxides. Excess supply of oxygen, pentoxides. If the oxidation state is more, so if I like compare N2O3 versus N2O5, greater the oxidation state, greater will be the acidic strength or acidic nature. At the same time, if I compare N2O5 versus P2O5, so what did I say first? Here to here, as the oxidation state increases from +3 to +5 for the same element, as the oxidation state increases, questions are asked like this, like we are not come to group 17, say like HCl, O2, O3, O4 for the same element. As the oxidation number increases down the group, acidic strength also increases. One thing. Very important, this question, especially. Next. Now, I have the same oxidation number +5. Now, nitrogen versus phosphorus. Nitrogen is more electronegative. Greater the electronegativity, greater will be the acidic nature. Means N2O5 will be more acidic than P2O5. Acidic strength here down the group increases. Acidic strength decreases. Still N2O5. Yes, correct. N2O3 versus N2O5. Both nitrogen plus 3 plus 5, N2O5. N2O5, P2O5, still N2O5. Nitrogen is more electronegative than phosphorus. Very good. As electronegativity decreases, acidic strength decreases. Plus 3 plus 5, acidic strength increases. The same thing. Have a look. Fine. N2O5 is quite stable while B2O5 obvious. Bi will not be very stable in the +5 state. So stability of the oxides of higher oxidation state decreases down the group. As mentioned, N2O and I didn't, you only mentioned. Sorry. N2O and NO are neutral in nature. Students, these elements are quite large in size. They cannot afford forming sideways overlap and pi bond. What they will do? They will form dimers like P2O3 combines with another P2O3 to form P4O6. Similarly, P4O6 and P4O10. I know it's written E, but it's mostly the, as I told, this nitrogen and phosphorus, we have to give it more importance than the other elements. You also know that. So we should know the structure of P2, I'm sorry, P4O6 and P4O10. How should we draw that? POP P4O4 5 and 6. P4O6. Got it? P4O6. Okay. If I have to change this only to P4O10, what should I do? I'll do it
Add
here
double
only. I'm not
bond of
going to redraw, huh?
add double
1,
Peroxide.
bond to
2, 3, and 4. Done. Correct. Fine. So when there's limited amount of oxygen, P4O6 is formed. When there's excess supply of oxygen, P4O10 is formed. Students, very important. Hydrides of group 15. A lot of questions are asked from this. Nitrogen plus hydrogen Haber's process ammonia is formed. Similarly, the other hydrides NH3, PH3, ASH3, SBH3, BiH3. All these hydrides are colorless gases. sp3 hybridized, one lone pair, three bond pairs, pyramidal in shape. Poisonous nature, okay. Increases from NH3 to BiH3. Due to hydrogen bonding, NH3 is soluble in water. It can form hydrogen bonds with water and hence water soluble. The other hydrides are less soluble. Tell me a simple thing. One must be there in the next slide, so I don't want to show you people there. Ammonia to BiH3. Comment on the basic nature of NH3 versus, means the trend down the group. It's a regular trend, either increases or decreases. BH3, why it should be highly soluble? NH3 is highly soluble, NH3, due to hydrogen bonding. I'm asking you the basic strength. How does it vary? Down the group decreases. So many people are saying decreases. What is the reason? Oh, first of all, wait. I Yeah, it decreases. But why does it decrease? Drago's rule, yes. We can. Yes. Drago's rule applicable, phosphorus onwards, yes. Okay. I'll have a simple agreed as character and all. Okay. Fine. I'll give a simple explanation. So, students, what happens to the lone pair? Greater the availability of the lone pair, greater is the Lewis base strength. When we are talking about the basic strength, we are talking basically about the Lewis base strength. So, very, very good. It can be explained by Drago's rule, and I'm extremely happy the way you people are answering. Ex- yes, coming back to the point. Mesmerized by the answers, yes. Yeah, coming back to the point, you can think like this. So, greater the availability of the lone pair on the central atom, greater is its Lewis base strength. What happens in the case of ammonia is nitrogen is small in size. So the lone pair is present in a very compact way, very small space. The same lone pair in Basm, here it's very compact arrangement. The lone pair is here like this. The arrangement is quite compact in nitrogen, so it's like more available. In other cases, big fat fellows they are. This big. I should draw bismuth also large. I saw no space. So this lone pair is now present in a larger orbital. So it's like more diffuse, means scattered. So its availability is comparatively less. Can also be one of the plausible explanations for it. Okay, so what happens is that the lone pair is present in a very compact way in nitrogen because of its small size, whereas it's quite scattered in the case of bismuth. I'm just comparing the first and last one so that you get the trend, and hence lone pair is more available in the first case. Basic strength more, yes. I would definitely appreciate your Drago's rule angle. No time to elaborate, but in case someone has sometimes some doubts towards then, we can discuss. Very good. Now, hydrides. Basic strength decreases because the lone pair is more scattered or diffused rather than being very compact in the case of NH3. Bond angle. Help me out with the bond angle. This also again chemical bonding. Nitrogen is much more electronegative than hydrogen. So the lone pair is present quite close to nitrogen. Very good, bond angle decreases. The reason nitrogen is much more electronegative than hydrogen, so all the lone pairs are crowding around nitrogen. Bond pair bonded repulsions are high. To minimize that, they are trying to little move away. So the bond angle in NH3 is little more than that in SBH3. In SBH3, the lone pair is almost here, quite far away. So the repulsion is less. It need not further go a little away from each other. The bond angle in ammonia will be more because they have to move away a little bit to minimize the bond pair repulsions because they're quite close. So bond angle decreases, agreed. A bond length, of course, increases because the antimony is quite large than hydrogen in the smallest element. The extent of overlap will be less. Bond strength less, bond length more, bond strength less, thermal stability also less, bond length more. Now, since bond strength is less, re- reducing nature will be more. The hydrogen here will be easily available. Reducing strength or reducing nature increases. Due to lack of compatibility, the hydrogens are more available. So they can supply its hydrogen because the bond is not strong. So thermal stability decreases, reducing nature increases, bond length is more, large in size. No, antimony is this big, hydrogen is this bond. Orbitals are large in size, bond length is more. Bond angle is less due to this explanation difference in electronegativity. If the central atom is more electronegative than the side atoms, bond angle decreases with decrease in electronegativity. Chemical bonding. Basic strength. The lone pair here is more spread out, diffused. It's not that available as in NH3. Basic strength decreases. Once again. Ha. Students here. No, okay. Students here. Yes. Decrease in basic strength. Agreed, agreed. I will once check the experimental values of melting and boiling point here, honestly, because they are experimental facts expected due to hydrogen bonding. And I would like to check the actual order of melt. Okay, okay, okay. Now it's okay. I saw that. I didn't see the animation. I saw that slide and I was not convinced. One second. So what happens is due to hydrogen bonding. See, these two NH3 and SbH3 have the edge over the other two in melting and boiling point. You know why? This SbH3 is large in size. When the atoms are large in size, no, the surface area is more, the van der Waals forces are stronger. So if you have a large size, the bond strength should be more, not if you not SbH bond strength, the bonding between one sp3 and another SbH3. This van der Waals forces should be stronger. SbH bond strength within the molecule is weak, but SbH3 linkage. SbH3, SbH3. This bonding is strong because of greater surface area, more van der Waals interaction. And this gets the edge due to hydrogen bonding. So here you have the edge of large size, high van der Waals forces. But which one dominates? Experimental decision. Here, the advantage of hydrogen bonding. So these two, any one of these two should have high melting point. And whether this value is not experimentally determined, whether the hydrogen bonding thing will get edge or our large size and more van der Waals forces will get edge has to be seriously. The teacher also says after looking into the experimental value. Okay, good. Hydrogen bonding gets a preference. I'll be happy. So after NH3, it's SbH3. So first hydrogen bonding gets preference and then size. So SbH3 after that, then ASH3 and PH3. Okay, justified. I'm the happiest. It's very logical. Let's see any anomalies there in the boiling point or not. If I'm not wrong, my memory says it's SbH3, then NH3, then ASH3, and then PH3. This two gets reversed in the boiling point. Let's see. Ah, see here hydrogen bonding gets preference, not always. Here size is getting preference as I say. The actual one is based on experimental order, we have to remember this. Mainly the boiling point one, exam wise, it's SbH3, then NH3. Remaining two, no problem. ASH3, PH3 the least. Hydrogen bonding gets preference here. Here, large size, more van der Waals forces. Make a note of it. Extremely important, right? This was very usual for both. First hydrogen bonding and rest as usual. Small size, less, large size more, except hydrogen bonding bring it front. But here in boiling point, I remember it is SbH3 which will come first and then ammonia goes and then the usual trend. We have to remember this. Remember this, please. And this one, this slide is also the previous one. Very important. This halides. Limited supply EX3. EX5, excess of halogen. NF3 is the only stable trihalide of halogen. Nitrogen small, fluorine small, manageable. NCl3, chlorine is quite larger, forget bromine and iodine. So they are going to be quite unstable due to large size of these halogen around this such a small nitrogen atom. No d orbitals to expand its octet. So NX5. This E cannot be nitrogen. No chance. Bismuth. Again, the small bismuth accommodating large chlorine, bromine, iodine around it. Not possible. As such, bismuth is not stable in the +5 state. Somehow, to some extent, though +5 is not that stable, BiF5. Because of small size and high electronegative, yes, size, yes. Fluorine, that's possible. D orbital contraction, excellent. So, what is d orbital contraction? Why PF5? This I can discuss now. P phosphorus. Yesterday, that's what I was waiting for. Then in this group 15, we'll discuss very briefly. PF5 is possible. PH5 isn't. What happens in PF5? P is delta plus. Due to this delta plus on P of PF5. Yes, a positive charge is generated or present on the phosphorus, and this delta plus deficiency, it attracts those electrons at d orbitals, and hence the d orbital comes closer. And you know, for hybridization, what is essential? That orbitals with similar energies should undergo hybridization. So S, P, and the D bring closer. It doesn't happen here because almost the electronegativity values of phosphorus and hydrogen are similar. So you don't get sufficient delta plus on the phosphorus. Here, the phosphorus is sufficiently delta plus. The delta plus phosphorus attracts the d electrons and hence d orbitals closer to it. So it's easy for it to undergo hybridization and form PCl5, PF5, etc. etc. Very good. And for similar reasons, you can think of PF5 also existing, but chlorine again becomes quite large in size. Forget bromine and iodine. And so the other pentahalides of bismuth do not exist. Trihalides except BiF3. BiF3 sufficiently ionic, small size, high electronegativity, and bismuth and fluorine will have sufficient electronegativity. I was telling in your batch only, right? If the electronegativity difference is greater than 1.7, then it can easily form ionic bonds. Nitrogen's preparation, fractional distillation of air. Yes. NH4Cl and NaNO2 will combine to form NH4NO2, which on heating will produce N2 gas. Students, if I have taken, suppose if I have taken NH4NO3, I hope you know this is ammonium nitrite. This is ammonium nitrate. What will happen here? Think. No, not it's remove water, remove to water. Students, N2O is formed. N2O. Fine. What is formed is N2O. I was trying to draw the structure of N2O that's going on in my mind. Why not write it? Students, ammonium nitrate produces N2O gas. Ammonium nitrite produces N2 gas. Yes, though right now we are talking about the preparation of N2, but this is also anyways related to our chapter only. Sorry. So 1, 2, 3, 4, 5. 1, 2, 3, 4. This will have a plus. 1, 2, 3, 4, 5, 6, 7. Minus. Can I write N2O this way? NO and NO2 I've already drawn. Can I draw N2O this way? I can, right? Can I show resonance? Lone to pi. At the same time, pi to lone. One, two. Agreed? Okay, okay, okay. This is writing yes, yes, yes. What's the hybridization of the central nitrogen? I have to just open my mouth to ask questions and I get all the correct answers. Yes, absolutely. It is sp hybridized. Excellent. So ammonium nitrite. Be careful. Nitrate will give you N2O. Just now we saw. Ammonium nitrite will give N2. Ammonium dichromate will also liberate. So ammonium dichromate is orange, and after the reaction, Cr2O3 is green in color. It's like the holy colors. It gives me a feeling. Lovely. N2 is formed. Azides. What's an azide anion, by the way? N3 minus is nitride ion. Every time there's a confusion among the students. Whereas N3, 3 nitrogen with one. Your one nitrogen is carrying 3 extra electrons. Nitride. Here, 3 nitrogens carry one negative charge. Azide ion. We'll try to draw azide ion. Let's see. There's one minus only, right? Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Wait. A minus here. A minus here. This will also do. Plus minus gets cancelled. You overall have a minus sign. Will do, no? Azide ion. This is the way you write yourself, you learn. Okay, fine. Uses of nitrogen. Liquid nitrogen as a refrigerant, etc. etc. Fine, you can go through. Okay, it's already there. Students, ammonium salts. When they react with bases, ammonia is liberated. Um, all ammonium salts, when they react with bases, let me think of ammonium sulfate reacting with NaOH, giving us Na2SO4, 2NH3 plus H2O. So ammonium salts, when they are heated with alkalis. Ammonium salts, when they are heated with alkalis, ammonia gas is liberated. Here you see, it's already there. When urea is undergoing hydrolysis, it forms ammonium carbonate, which dissociates, giving NH3, H2O, and CO2. So from organic matter, urea, its hydrolysis produces ammonium carbonate, which basically splits into ammonia, water, and CO2. All ammonium salts will react with alkalis to liberate ammonia gas, the lab method of preparation. Fine. Ammonia. Okay, this was only given. Then no, okay. Haber's process, not to forget the Na2SO4. I have to put a 2 here and a 2 here. That's fine. And a 2 here as well. Fine. Balancing right now is not so significant. Haber's process. I have no words. Tell me. I'll ask a question on equilibrium. So if I want production of more ammonia, what conditions of temperature and pressure would be suitable? Think from the Le-Chatelier's viewpoint. High pressure. So if I apply high pressure, someone is writing in the chats. So if I apply high pressure, the reaction should move in a direction where the gaseous moles are less done. So in this reaction, there are 4 gaseous moles in the reactant site and 2 gaseous moles in the product side. 4 gaseous moles in the reactant side, 2 gaseous moles in the product side. So the reaction should move in a direction that the gaseous moles are less. So high temperature forward, since the reaction is exothermic, low temperature forward, low temperature, high pressure. Good. I was analyzing till then, and now, yes. Low temperature exothermic reactions are favored in forward direction at low temperature. High pressure favors the equilibrium in a direction where the gaseous moles are less. Yes, so high temperature, low pressure. What did I say? What did I say? High pressure, I'm sorry, extremely sorry. High pressure, forward. Low temperature, forward. Catalyst, it'll just increase the rate of both forward and backward reaction to the same extent such that the equilibrium constant's value doesn't change, right? It will increase the rate of both forward and backward direction to the same extent. If you remember, equilibrium constant K is Kf by Kb. So Kf and Kb will be increased in a way or an extent so that the K equilibrium will not change unless and until temperature changes. Yes, iron is a catalyst, finely divided Fe is a catalyst, and molybdenum is used as a promoter. Fine, clear? All these things are known. Students, tell me, if some inert gas is added to this reaction mixture at constant volume, the equilibrium will be shifted more in which direction? Or what do you have to comment on this? So if it's inert gas at constant volume, someone is telling that there's no effect on equilibrium, and is she correct? Yes, correct. What if inert gas is added, but at constant pressure. Inert gas is added at not constant volume, no effect, done, over. At constant pressure. When inert gas is added at constant pressure, I said. Pressure is kept constant, volume will increase. Volume is, so N by V stands for this concentration. So what happens is if you're not if changing the pressure is constant, the volume will be more. The volume will be more. The number of gaseous moles also has to be more so that N by V remains constant. And hence, very good. Very good. So if pressure is constant, V will be more. V will be more so that the N by V ratio unchanged is remains unchanged. Pressure is more. I'm sorry. Pressure is constant, volume will be more. This is more so that the ratio is not disturbed, N should be more. The reaction should move in a direction where the gaseous moles are more, which means backward. So addition of inert gas at constant volume, no change in equilibrium. Addition of inert gas at constant pressure, backward reaction takes place. Very good, students. God bless you with these skills in the exam to analyze the things fast in an effective way. So nice. Weakly basic in nature when you dissolve it in water, no? NH4OH, which is formed as weakly basic in nature. It can react with acids like HCl to form ammonium chloride salt, dense white fumes, ammonium sulfate with H2SO4. Ammonium hydroxide with zinc sulfate. Zinc hydroxide is white precipitate. No, it's okay. Ferric hydroxide is a brown precipitate. Color of these precipitates. Copper sulfate solution. To copper sulfate solution, when you add excess of NH4OH solution, ammonia solution, a deep blue coloration will be obtained due to the formation of this complex. A white precipitate of AgCl is formed when NaCl reacts with AgNO3. This white precipitate will dissolve in excess of ammonia to form AgNH3 whole twice Cl, a colorless complex. So white precipitate of AgCl will dissolve in excess of ammonia forming a colorless complex. Blue solution of copper sulfate will dissolve in excess of ammonia to form a deep blue complex. These questions are usually asked. The formula, the color should be known. Oxides of nitrogen. I wanted these structures to be here. Understood? Yes, we can place a coordinate bond also. This is the odd electron. This is NO2. NO2 is paramagnetic. Can react with another NO2 molecule or basically dimerize to form N2O4. N2O4 exists at low temperature, liquid, reddish brown liquid, low temperature. At high temperature, it exists as NO2 gas, reddish brown. This is N2O4. This is the structure of N2O3. 88 means octet is satisfied, is being shown. And this is N2O5. Here you have N2O5, N2O3, NO2, sorry, NO2 here, N2O4 here, NO here, NO2, N2O here. Everything here. Out of that, NO and NO2 are paramagnetic, as we have seen also when drawing. I mentioned NH4NO3's decomposition producing N2O. Nitrite ion plus Fe2 plus ion producing NO. So many reactions are there. See if you can remember the preparation. Otherwise, focus more on the structure, hybridization, which is dia, which is para. That also would be good enough. Because so many things are there. Yes, remember one more fact that these two are neutral as mentioned here. Remaining all of them are acidic, which is colored, which is colorless, colorless, colorless. This reddish brown gas is blue solid. These two remaining are colorless solid. So that is also another important thing. Give me a minute, students. Just thank you so much. Nitric acid. Students, nitric acid can act as an oxidizing agent, reducing agent both, or only as dash 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 agent. Oxidizing agent, nitrogen is present in its highest possible oxidation state. Yes. Only oxidizing agent, because it oxidizing agent gets reduced, but a reducing agent gets oxidized. This can't get oxidized or lose electrons further. Fine. Okay. It only acts as oxidizing agent. By the way, it's a strong, very strong oxidizing agent. So in the lab, H2SO4, concentrated H2SO4 is heated with KNO3 or NaNO3, and HNO3 is produced. Can you recollect one thing? Can I correlate with something with physical chemistry? I can recollect azeotropes. HNO3 solution of a certain concentration forms azeotropes, no? A particular percent, very good. I got some response. A particular percentage of HNO3 solution forms azeotrope, means I can't remove any further water from HNO3 at that point of time, means it forms a constant boiling mixture where distillation also further can't separate it. By the way, it forms low boil 68% H2SO4. So nice. Yes, that's correct. By the way, it forms maximum boiling azeotrope or minimum boiling azeotrope. Think. I someone 68% H2SO4. I'm sorry. 68% HNO3 forms minimum on 2 maximum, 2 minimum. What should I do? Tell me. Solutions showing negative deviation from maximum boiling azeotrope. Yes, this one is maximum boiling azeotrope, and yes, ethanol water. They show positive deviation. They will form minimum boiling azeotrope. Good. I was just randomly trying to check also. I have very less time to check any other things, but my target, yeah, I'm assigned for syllabus completion. Okay, good. Randomly, if I check also, good. True to the words. They are very good students. So ammonia gets oxidized in the presence of platinum catalyst, this temperature, this pressure, and NO is formed. Oswald's method. So ammonia and air. When this mixture is passed over platinum gauge catalyst at 500 Kelvin, ammonia is oxidized to nitric oxide. Then nitric oxide is oxidized to nitrogen dioxide, and NO2 is a mixed anhydride. You know this? Anhydride generally means the particular oxide of substance plus water, say CO2, is the acid anhydride of carbonic acid. Just add water to it, you get carbonic acid. So we can call it acid anhydride. SO3 similarly is an acid anhydride of H2SO4. Yes. But NO2, if you add water to it, no, it forms HNO2 plus HNO3. But HNO3 being unstable dissociates to NO again. That's the reason NO is written. So what happens is HNO, a minute, NO2 and water. They produce HNO3 and HNO2. But this HNO2 is unstable. It disproportionates giving HNO3 and NO. So overall, if I see NO2 plus H2O, this gets cancelled, gives me finally HNO3 and NO. As I was telling, 68% H2, I'm sorry again, I'm saying H2. 68% HNO3 forms minimum or maximum, just now we discussed, maximum boiling azeotrope. Nitric acid is very important, students. You keep it for some time, some of it dissociates to liberate NO2, and the solution doesn't remain colorless at all. It turns yellow in color. It's a very powerful oxidizing agent. Less than 2% is very, very dilute HNO3. 6% very dilute. 20% dilute. More than that, concentrated. Basically 50 to 70. Not only above 70, 50% also I call it concentrated only. 20% dilute, 6% very dilute, 2% very, very dilute. So here you have to memorize that. It's concentrated, we get NO2. Dilute, I'm getting here N2, and very, very dilute, I'm getting NH4NO3. Or the next click, yes. Here NO2, NO, no reaction. You have to remember this. This, not these. Very important. Because it's a very strong oxidizing agent. An oxide coating is formed on the surface of aluminum, you must be knowing. Utensils which we use. And that's the reason FeAlCr, they do not dissolve in concentrated nitric acid, because of the protective film on the surface of these elements. Aluminium contains a protective oxide coating. Aluminium is highly reactive. It reacts with the oxygen, forms the aluminium oxide coating on its surface. Concentrated HNO3 cannot dissolve noble metals like gold and aluminium. For that, you need aqua regia. Concentrated HCl and concentrated HNO3 in the 3:1 ratio. So, aqua regia can dissolve noble metals like gold and platinum, not even very concentrated HNO3. NM for non-metals. It will oxidize the non-metals to the concentrated one. Will oxidize the non-metals to its highest oxidation state. Like carbon will be oxidized to C+4, carbonic acid. No reaction with dilute acids. Yes. So boron will be oxidized to boron plus 3, boric acid. Carbon to carbon plus 4, carbonic acid. Phosphorus to phosphoric acid, H3PO4. Sulfur to sulfuric acid. So the concentrated HNO3 is such a strong oxidizing agent, the non-metal would be oxidized to its highest oxidation state. Non-metal would be oxidized to its highest oxidation state. Can we quickly recollect? Copper with very, very dilute HNO3, no reaction. But zinc with very, very dilute HNO3, NH4NO3. Zinc with dilute HNO3, N2O or NO? N2O. Concentrated NO2. NO2, copper plus concentrated HNO3, NO2. Copper plus dilute HNO3, NO. Copper with very, very dilute HNO3, no reaction. Good. Good response. Very good. Arsenic is oxidized to its +5 oxidation state. Except bismuth, the +5 state is more stable. You can see what are the uses. Students, something very important written here. White phosphorus, which is P4, and due to the angle strain, it's very, very reactive. This P4, when it reacts with NaOH, this reaction is important. It undergoes disproportionation to pH3 and NaH2PO2. So phosphorus in its zero oxidation state produces phosphorus +1. Shit, what happened? Okay, sorry, it's okay now. Phosphorus 0 undergoes oxidation and forms phosphorus +1. Loses 0 to +1 loss, 0 to -3 gain. So phosphorus here undergoes disproportionation. This reaction is an important method for the preparation of phosphine. This reaction is an important method to show the disproportionation reaction in P4 in the presence of alkali. Phosphorus glows in the dark, and I can see so many covalent bonds. So I can see it basically insoluble in water but soluble in carbon disulfide. This reaction is important. P4 plus NaOH plus water giving pH3 plus Na2. Why? Sorry, not Na2, NaH2. Why Na2 is not possible? Just now we discussed its N factor is 1. So it's only possible to replace, this 2 will be intact, the hydrogen here with sodium. So NaH2PO2. This proportionation here. The comparison between red phosphorus and white black phosphorus, and the most stable allotrope of phosphorus is the black phosphorus. That also, anyone, any idea, the beta black or the alpha black, which is the most stable form? Red phosphorus is obtained when the different P4 units are linked together. White is P4, very reactive. Shows disproportionation you saw just now. That's also the method of preparation of phosphine. Fine. Red phosphorus. When you are heating white phosphorus at high temperature, the P4 units combine together, and now it doesn't glow in the dark. It's red phosphorus, as you can see, and so on. Now, black phosphorus is the most stable allotrope of phosphorus. The beta black phosphorus is obtained by heating white phosphorus at around 473 Kelvin. Beta, someone, only Karthik has answered. What about others? There's no harm in attempting. You'll find out otherwise. I want to know. While the red phosphorus, on heating it around 800 Kelvin, produces the alpha black phosphorus, which is more reactive. Karthik says beta. Others? Black is the, not black phosphorus is the most stable allotrope of phosphorus. It has two forms, alpha black and beta black. Others are not telling anything, so what will I tell? Alpha or beta? Tell. Then we can at least go with the majority, or at least know what majority is thinking. So students, here you can see, think. think before the class and tell me or find out. Alpha, alpha. What happened to this mouse? Beta. 2 alpha, 2 beta. I can't again answer. Gone. You have to wait. So phosphorus trioxide is formed when phosphorus is burnt in limited supply of oxygen. Limited supply P4O6. Excess ox. When P4O6 is now treated with limited supply of oxygen, or P is treated with excess of oxygen, P4O10. P4 limited supply P4O6, excess supply P4O10. The structures I've drawn. POP, 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 POP linkages and a double bond, double bond, double bond, double bond. This double bonds, if you remove, it becomes P4O6. P4O10 dissolves in cold water to produce metaphosphoric acid. Now, since it's time, I'll not hurry with the phosphorus part. There's no reason to hurry so much. Hurrying is going fast is important. Alpha is more stable. Alpha is obtained from white phosphorus. Beta is obtained from a red phosphorus. So, no, black is more stable than red. It's not red phosphorus. The question is, it's alpha black form or beta black form, which is the more stable allotrope. Karthik now says alpha. I've got a mix of alpha and beta. So I'll give you time to find out tomorrow. That's what will be the first question. Once again, let me draw the structure of P4O6. How many POP linkages are there, etc., etc. Such questions are asked. So if this is P4O6, and if I just mention the presence of 4 double bonds here, P4O10. Fine. It's already time. There's no point in hurrying. Again with phosphorus and its compounds and oxyacids. We'll continue our discussion in the next class. And my question remains the same. You have to tell me which is the most stable allotrope of, you can find it out meanwhile. Phosphorus, is it the alpha black? Pretty sure alpha black. Others, no one is like challenging. No one is challenging. It's time, students. It's time. And I have to leave. So this is now the class. So that's the reason I have to say bye-bye to you. Okay. Thank you all. I've given a homework. So right now I've said I'll tell you tomorrow. Okay, then bye. It's time. I have to leave. Thank you all. Bye.